Bismillah Rahman Rahim. Now in this we discussed so far how to calculate the depth before and after the jump. So you can see here that these equations we can use for rectangular channel, how to calculate the depth before and after the jump. Clear? Now to continue with this, as we already know that there is the head loss. So this head loss, if we want to calculate, so the head loss that is caused by the jump is this. You can see the drop in energy from section 1 to section 2. So this will be equal to this energy loss in the hydraulic jump. So this is for any channel. This equation is applicable to any channel, including this rectangular channel also. So for this case, this HL head loss for the jump HLJ, this is equal to E1 minus E2. So this can be written as Y1 plus V1 square by 2G, and this is Y2 plus V2 square divided by 2G. This is in general we can apply to any channel. Also for rectangular channel, we can simplify this. For rectangular channel, so this HLJ, this is equal to Y2 minus Y1, this is cube divided by 4 times Y1 and Y2. This equation we can prove for a rectangular channel. So you use the above equation, either this one or this one, you will get the same answer. Clear? This is for rectangular channel. The below equation is applicable. Now we come to this figure. We discuss the basic concepts. So you see here that in this case, this is Y1 and Y2, and for the same specific force we have these two depths, and these are known as the alternate depths. Clear? So these alternate depths that we can determine, you see here that we have Y1. This Y1, it is already here at point E. So now this Y1, we proceed here, it will cut this specific energy, specific force curve here. This is specific energy E point here, and now this specific force, this is point A. Now we see that the specific force, it is the same before and after the jump. So this is the same. That's why we proceed up. So we proceed up on this line and we get this point B. So this point B is actually this Y2, and this point, if we extend here, this is that Y2, same point here on the specific energy curve. This B here, this is this C point here, and this is the jump. This is the hydraulic jump, the depth from subcritical depth, this supercritical depth to subcritical depth here. Now you see here that in this diagram, the depth is transposed to the specific energy diagram, and we can determine V square by 2G. So how we can determine? This is your V square by 2G here. This is your V square by 2G. So this V2 square by 2G, this is given by this line here, CD. This CD, you see here, this is the same as this V2 square by 2G. Just vertically here, and this is V2 square by 2G. This is how you can determine V2 square by 2G. This V1 square by 2G, this one here, V1 square by 2G, this is EF. You can see here, this is F, this is F here, and this is E here. So it means this distance EF, this is actually your V1 square by 2G. Clear? And if we are interested to calculate the head loss, so the head loss is what? It is the difference, this CG, this line CG here, this is the head loss. If I remove here this one, this CG, you can see here, this CG, this is your head loss, because this is the energy at this second section and this is the energy at the first section. So this CG is actually your change in the specific energy, which is the head loss. So this CG, and this is also equal to this FH. You see here, this is H and this is F. So this here FH, this is same here as your HL. So now you can see that specific energy curve together with the specific force curve, we are able to calculate all the parameters. Clear? Now this figure, which is here, the scale is shown. Remember, these both curves, these are plotted for the condition of 2 CFS per foot of width. That's why you see the values here. Now in this figure, what we did is that we have this Y1, which is here. You have the specific energy here. So this is your Y1, and then for the same specific force, we come here because the specific force is the same before and after the jump, and then we are coming here and we determine this Y2. Now this Y2 and Y1, these are conjugate depths, as we already explained. Y1 is the conjugate depth of Y2 and Y2 is the conjugate depth of Y1. Clear? Now this YC, we already discussed that this is the critical depth. At this point, the specific energy is minimum, and this is the same as this point. This is also YC. You see here. So at the critical depth, clear? At the critical depth, so we have the minimum specific force, and also we have the minimum specific energy. And at the critical depth, the discharge will be maximum. So applications of the hydraulic jump. Now, as I said, this hydraulic jump is desirable actually for different applications. So we already highlighted that it is used as energy dissipator. It reduces the velocity and prevent erosion. Clear? Raise the water level for irrigation or water distribution purposes, as we already discussed that the depth after the hydraulic jump is more, clear, to the depth before the jump. Similarly, it increases weight on apron by raising the depth of water to prevent uplift pressure. Now these are the concepts that actually you will study in another course, not here. For example, we have this spillway, and the water flows over the spillway. So what will happen is this water flows over the spillway with very high velocity, as we just saw. Now, because of this, the hydraulic jump forms. After this, we have the hydraulic jump, and then the water flows with more depth here. So downstream of this spillway, this protection is provided here. Downstream of the spillway here, we have to provide the protection so that this high velocity water does not cause damage to the bed of the channel. And as a result of hydraulic jump, the energy is dissipated, but there will be turbulence in the hydraulic jump also. So we have to provide protection against that also. So on the downstream side of the spillway, this apron is provided here. This is known as apron. I will show you the pictures. This is known as the apron. And in here, because you study geotechnical engineering, there will be pore water pressure. So there will be an uplift pressure acting against it. There will be uplift pressure. This you will study in detail in irrigation engineering. So because of hydraulic jump, the depth increases. So that's why it says that increase weight on apron by raising the depth of water to prevent the uplift pressure. So because here the water depth increases, it will counteract this uplift pressure. So you can see it is a positive. It is desirable. Clear? So this is the application of hydraulic jump. Clear? Similarly, because of hydraulic jump, we have turbulence. So that's why this hydraulic jump is helpful in mixing the chemical substances in water treatment processes. This you will study in detail in environmental engineering course. In water treatment plants, we use different chemicals for purification of the water. So this hydraulic jump, it helps to create the turbulence, and it can help to effectively mix the chemical substances. And also because we have turbulence, so this hydraulic jump, it can help aeration of the flow. And because of aeration, what will happen? It will help to increase the concentration of dissolved oxygen which is required. Clear? So these 4 and 5, this you will study in detail in environmental engineering, where you study different water treatment processes, water treatment plants. Clear? So you can see here that hydraulic jump, it has many applications. These are just a few mentioned here. There can be other applications of hydraulic jump also, but you can see that this hydraulic jump, it is desirable. Clear? That's why we need to study how to do the analysis of hydraulic jump. Now we have different types of hydraulic jump. So this classification which is given, this is given in your textbook, this table. So these jumps can be divided into undular jump, weak jump, oscillating jump, steady jump, strong jump. And based on the criteria of the Froude number, this is F1. It means the Froude number at the upstream of the hydraulic jump. So if the Froude number is 1 to 1.7, we will say it is undular jump. And the energy dissipation, because we say that there is dissipation of energy as a result of the hydraulic jump, it is less than 5%. Clear? If we have weak jump, then the Froude number ranges 1.7 to 2.5, and 5 to 15% energy is dissipated, depending on the conditions. Clear? Similarly, we have oscillating jump. 15 to 45% of the energy is dissipated, but this is unstable. We have to avoid this type of jump. The reason is that in this case, the oscillating jump, this to be avoided. The main stream of water flowing through the jump oscillates between the bed and the surface of water. So these generate waves that can be damaging for great distances downstream. It says that when we have this oscillating jump, you have this bed of the channel, and when we have this is the jump which is created. So what will happen is that when the water flows, it oscillates between the surface, and the bed. Clear? It will oscillate between the two. So that's why it is written in your textbook that it will oscillate between the bed and the surface, that will generate the waves, and that can be damaging for greater distances downstream. So that's why in the design we have to avoid this, clear, oscillating jump. And we have steady jump where the Froude number range is 4.5 to 9, and energy dissipation is 45 to 70%. And for strong jump, Froude number greater than 9, this is F1, clear, upstream of the jump, remember, and energy dissipation is 70 to 85%. Choppy intermittent small waves, clear. And if you want to see, so these are the figures which are given in fluid mechanics books. This is the relative comparison. You can visualize that we have undular jump. This is how the undular jump looks like. Then we have the weak jump, we have the oscillating jump. You can see here in oscillating jump, so it oscillates, you see, on the downstream and the up. So that's why it is mentioned that in the design we have to avoid occurrence of this type of jump, clear. And we have steady jump, and then we have the strong jump. So this is a relative comparison of the different types of jumps, clear. Now in this here you see that we have this Froude number 1.2 and Froude number 1.6. You can see here the waves of the surface, the jump which is created. But this is which category here? Undular jump, 1 to 1.7. You can see here 1 to 1.7, that is classified as undular jump. So less than 5% of energy will be dissipated here. You can see here, because of this not much energy will be dissipated from these figures. Then you can see the steady jump, clear. This is the steady jump. So the steady jump that we study here, in the steady jump, 45 to 70% of the energy is dissipated. And the range for this type of hydraulic jump, 4.5 to 9, clear. 45 to 70% of the energy is dissipated. Strong jump up to 85%. You can see here from 70 to 85%. So you can see here that in this case steady jump, and this is the strong jump up to 85%. You see here the energy will be dissipated. So which type of jump? This, you know, when we design the hydraulic structure, so we later on towards the end of this lecture we will study a topic when we provide the protection downstream of the hydraulic structure, what type of jump will occur under what conditions. So actually this we have to take care when we design the hydraulic structures, clear, the detailed design. Now I will show you some video of this. We discuss some basic concepts. So you can see here, this is the hydraulic jump. Water depth changes from supercritical to subcritical. This is hydraulic jump.
सर ये oscillating jump है.
This will depend on the condition. Like this you cannot say. This is in the Tarbela Dam. You see here that the water is released through the tunnels to dissipate the energy.
सर हम डायरेक्ट नहीं कह सकते कि ये ऑसिलेटिंग जंप है या स्टेडी जंप है
No, like
या
this you cannot. You have to determine the characteristics of that jump.
जी सर
Now in here we have the hydraulic jump. This is an experiment how to determine the head loss. You can see here we have loss of energy. So how to experimentally determine this? This is for rectangular channel. Now you can see the water is flowing in a channel. We want to establish the hydraulic jump. Now you can see the hydraulic jump is established. Now we have to measure the upstream depth of the hydraulic jump. This is now the upstream depth of the hydraulic jump. Now next we will measure the depth downstream of the jump. This is now the downstream depth of the jump. This is now for a rectangular channel, as we already discussed. So you just need to measure the depth upstream and downstream of the jump, and this is how you can calculate the energy loss. So now in this case, you can see here that as you were discussing, you ask a question that it is what type of jump. You see here visually, it's very not easy to tell that, okay, this is what type of jump. So we have to check the characteristics. And then based on that, then we can determine that what type of jump is this. Clear? Okay. Next is important, that is length of hydraulic jump. So length of hydraulic jump, which is given in your textbook, it says that the length of hydraulic jump is difficult to predict. Clear? A good approximation for jump length is about length of the jump. So LJ, this is a good approximation. In your textbook, it is given 5 times y2. It is expressed as in terms of the depth after the jump. This is approximation, a good approximation. Clear? And it says that in most cases, only this is just written in your textbook, I will explain. In most cases, it says that we have 4 less than Lj by y2 same like this, and less than 6. So this is what is written in your textbook, that although the length of the jump is difficult to predict, but a good approximation is about 5 times y2. y2 is the depth after the jump. And then it says that in most cases between 4 and 6, this Lj by y2, this is y2, the depth after the jump. However, this is a graph which is developed by the USBR, US Bureau of Reclamation. They conducted large experiments on these hydraulic jumps, and even this classification is also given by USBR. This classification that we discussed, this is also given by USBR. You can read the footnote in your textbook. So what they did is that they conducted large experiments, and then they developed, you see here all types are there: undular jump, weak jump, oscillating jump, steady jump, strong jump. Clear? So what we see here is the ratio L by Y2, dimensionless, because when you develop dimensionless, it becomes independent of units. So we are not confused. This graph is now applicable for SI units, or this graph is applicable for British gravitational system. So that's why we like to develop graphs which are include dimensionless quantities. We will study later on dimension analysis. Now in this case, we have this Froude number. This is F1. This is Froude number. F1 means that it is upstream of the jump. Clear? So what we are trying to predict is this length of the jump here. Clear? So now for the different types, they conducted different experiments. You can see here for different Froude numbers. So they developed this here. For example, you want to determine the length of the jump. Primarily, this graph is developed for rectangular channels. Clear? Now, in this case, let's say, for example, the Froude number comes out to be 5. Upstream of the jump, you calculate the Froude number F1, and it comes out to be 5. So now you know that it is steady jump. You can see here, it is steady jump, and you will proceed up in this line, proceed up along here, and then it crosses here, this one, and then from here you proceed horizontally, and now read the graph value, which is 6. So it means L by Y2 is 6. So L will be equal to 6 times the depth after the jump. This is Y2, the depth after the jump. So now you can see even in this graph that this length of jump for the different types of hydraulic jump, it ranges between, you can see, 4 and 6. So that's why in your textbook it is written that in most cases that this Lj by Y2 is between 4 and 6. So you can see here that in your textbook it is correct. Clear? You see, in most of the cases it is between 4 and 6, this Lj by Y2. So this is how we estimate the depth of the hydraulic jump. Clear? Now this is actually an example given in your textbook where we are interested to calculate the location of the hydraulic jump. So now we are able to calculate length of the jump, how much energy is dissipated in the hydraulic jump, how to calculate the depth before the jump and the depth immediately after the jump. Now the next question that comes into mind is that how in the open channel flow problems we will locate the hydraulic jump. So this I will explain in this. We will solve also one problem to understand how we can locate now the hydraulic jump. By location means where it will occur. How you will know that this hydraulic jump will occur here. Clear? So this also we can calculate. Now in this figure I will try to explain that this case 1 and case 2 which are given, this figure is also from your textbook. So which one is correct? Now let us try to discuss this in detail, and actually we will solve one problem, but this discussion will help us to solve that problem. Now in this case you see that examples of the location of hydraulic jump where one conjugate depth is normal. It means that this is an example. This may not be always the case. This is just an example where it happens that one of the conjugate depth, either y1 or y2, happens to be the normal depth. Normal depth that we calculated in the uniform flow using the Manning's formula, or we apply the Chezy formula that we calculate. So this is just an example. It doesn't mean that always this will be the case. Clear? Okay, let us discuss this. Let us first discuss this case 2. Now in this case what happens is that we have a steep slope and we have a mild slope. So on a steep slope, you see here this normal depth, which we can calculate. How you can calculate the normal depth? By application of either Manning's formula or Chezy formula. But we are using Manning formula throughout the textbook. I already explained the reasons for that. So you apply the Manning's formula, you calculate the normal depth. Now on the normal depth, this is, let's say, your y1. Now you can calculate the conjugate depth. This is now the conjugate depth. Why? Because we are assuming this is the hydraulic jump, and this is the depth before the jump, and this will be then the depth after the jump. So you can apply the theory as we develop now the equations. So you can now calculate the depth, clear the conjugate depth. Now in this case, what will happen? This depth is now given, you can calculate this. We already developed the equation. If y1 is given, you can calculate y2. If y2 is given, you can calculate y1. And we are still discussing this for the rectangular channels. Now, what happens is that on a steep slope, this depth changes to y1 after the hydraulic jump. Now, we expect S1 curve here. We already studied the gradually varied water surface profiles. So we expect this S1. Why S1? S, because we have steep slope. So when we have steep slope, you will have S profile. When we have S profile, then there is a possibility it can be S1, S2, and S3. If you remember the previous lecture. So S1, because it is type 1. Why? Because you have this normal depth, and this dash line which we can calculate, this is critical depth. We already have the equation to calculate the critical depth. So now the depth is above the 2. When it is above the 2, it is type 1. So that's why we expect it to be S1 curve. Because now the depth here, it is above the normal depth and the critical depth. So we have S1 curve. Now if you let me go to here, we discussed this in water surface profiles. We have S1 because the depth is above the 2. It is above the critical depth and it is above the normal depth. So S1. If it was between the two, S2. Below the 2, S3. Now in this case, if this is going to occur, you have, let's say, the normal depth, then you have the hydraulic jump, then you have the S1 profile. If it has to occur, it means it is increasing slope. This S1 is increasing slope. That's why dy by dx is positive. So now if I come back here, if we say that we have S1 curve, it means that this curve will increase. As you can see here, it is increasing and it is further expected to increase here. Now when it crosses the break in the slope, this is the break in the slope. So the slope becomes mild slope. When the slope becomes mild slope, we cannot have S profile. Because for the mild slope, we must have M curves now. As we discuss here, for mild channels, for mild slope, we have M1, M2, M3. So now it means that after the curve, then we expect, because it is rising, this S1 is rising, and this is rising. Why it is rising? Because you see here, this is your critical depth, and you also can calculate the normal depth using the Manning's formula for the mild slope, just like we calculated here. So it means that this is a rising slope. Why it is rising slope? Because it will be above YC and Y0. Again, so we expect this to be M1 profile. We expect this to be M1 curve. Now, this M1 curve has to bring this depth to lower, because now at this point here you have this as the normal depth that we expect in the mild slope. So it means that this M1 has to bring this depth to this depth here. This is not possible because M1 is a rising profile. It cannot bring the depth from here to here. So that's why this type of profile cannot occur. This profile cannot occur. Let us explore this case 1. Now in this case, we determine this normal depth using the Manning's formula. The critical depth you can calculate using the equations that we already discussed. So you will get this dash dash line. Then you can calculate this normal depth, again apply the Manning's formula. Now for this normal depth, I calculate this y2 dash, which is the depth upstream of this. So this y2 dash is the conjugate depth of y02, and this y02 is the conjugate depth of y2. So how to calculate this y2 dash? This is what we discuss. So you calculate this. Now at this point here, the normal depth is here. We already calculated, and this y2 dash will be greater than this. Why? The reason is that this is the depth corresponding to steep slope. And when this depth comes here on a mild slope, it will try to increase. This is what we discuss here. I show you already in here, because if you remember, okay, maybe I remove it. Let me show it again here, or let me go to the figure. Let me go to the figure here. You see that we have this M3 profile. Now the depth is supercritical. But if your slope is mild, it will try to increase, because mild slope cannot sustain supercritical depth. So it will increase. So that's why in here, this depth will now increase to y2 dash, which is the conjugate depth of y02. So it means that we will have a rising curve here. This is a rising curve, and it is M3 curve. It is okay. Why? Because this is exactly similar to this case here. You see, this is M3. So this is possible. This is possible. And then after this, because the depth has to further increase to maintain the normal depth on a mild slope, it will pass through the critical depth. And as a result, this hydraulic jump can occur. And after the hydraulic jump, the water will flow with normal depth. This y1 dash that we calculated here, this is shown here. You see, it is not possible. This y1 dash is not possible, because the water will flow with the normal depth here. So it means that this is the possible condition. You have M3 curve, then after the break, this hydraulic jump will occur, and the water will then continue to flow on a mild slope with the normal depth, this one here. So it means this is the possible profile, and this is the correct situation. Now what I explain qualitatively, this is given by numerical values. You check the sample problem. This is sample problem 10.10 in your textbook. Sample problem 10.10. This is a solved example where they explain these figures. So by numerical values, you will see that this case 2 cannot occur, and this is the correct answer. Case 1 is possible, and this can occur. Now the next thing is the location of the hydraulic jump. I will solve another problem. This is already solved problem. You can solve by yourself. I already explained. There, from the numerical values, you will confirm what I'm explaining here. I will solve another problem to save time. And in here, you see that the hydraulic jump occurs here. Now we are looking for the location of the hydraulic jump. So now for this given problem and this associated figure which is given, so we say that this is now the correct possible situation. So now we are interested that it will occur after the break. This is the break in the slope. The hydraulic jump will occur after the break, but at how much distance? This is now the next question that we have to answer. So you see, you will get a problem. It will be stated, will the hydraulic jump occur or not? So first we have to determine that yes or no, the hydraulic jump will occur. Not occur, finish. If it is occur, then the next question will be at what distance from this point, from this section, at what distance it will occur. So this is what we have to answer right now. So now to answer this question here, this question, we have to combine the sections of gradually varied flow that we discuss with the rapidly varied flow. This is in the location of the jump, we have to combine these concepts. So we have to study gradually varied flow concepts. This we will combine with this rapidly varied flow, because you have to determine will the hydraulic jump occur. If occur, what is the depth before, after the jump. So you have to apply the concept that we studied in rapidly varied flow. But how you will apply this concept? This concept, actually you will calculate this by delta x. You remember in the last class we discussed this. So this coming from the gradually varied flow concept, this equation that we discuss, this we will use to find the location of the jump. Clear? This we will use, because this was equal to this delta x. This here we discuss. Clear? That delta x, that is equal to E1 minus E2 divided by S minus S naught. So this equation essentially we will use. So we are combining the concepts of the two that will help us to locate the hydraulic jump. So this is already applied in this problem also, and inshallah we will solve another problem. So further it will clarify our concepts. Clear? So you can see this solved problem. So this, with reference to this figure, then you can determine that which type of case is possible and which is not possible. Now we discuss the Stilling basin, the last of the topic here. So when water from elevated water bodies like reservoirs flows over spillways, this we already discussed, through outlet works or down chutes, it can have tremendous energy. As you already saw that when we have the spillway, this is, let's say, the spillway, and the water flows over this very high velocity, so it can damage the floor here. Clear? So it can have tremendous energy, and this energy can cause great damage to the structure itself, to the ground supporting the structure, and therefore ultimately to the structure itself and to the downstream channels. So it can be damaging. The hydraulic jump is one of most effective methods. You see, this is not the only method, is one of the most effective methods of dissipating such flow energy. But the hydraulic jumps themselves can also be very destructive. So what we do, we provide this Stilling basin. The objective of Stilling basin is to initiate a jump for energy dissipation and to contain it within a structure that will minimize damage. So what we do is that downstream of the hydraulic jumps, we provide these Stilling basin. I will show you the pictures. So they initiate the hydraulic jump and contain the hydraulic jump For example, what we do here is that at this point here we provide stilling basin that can be of different types. So it will initiate the hydraulic jump. This hydraulic jump will occur, and also it will contain, so that the water after this stilling basin flows with greater depth and to avoid any damage. This is known as the stilling basin. And the stilling basins, so these are generally reinforced concrete structures designed to contain the turbulent flow of a hydraulic jump. So these are made of reinforced cement concrete because they should be strong enough to contain this hydraulic jump. So the energy is dissipated, and also this is reinforced cement concrete. It will protect the channel bottom against erosion, and also it will increase the stability of this hydraulic structure, because if the material is removed due to erosion, it will pose threat to the stability of the hydraulic structure. So for this purpose, we provide these stilling basins. Let us now see this. The US Bureau of Reclamation, which we call USBR, has developed 10 types of stilling basin. If you study their documents, detailed documents, 10 types of stilling basin they develop for these hydraulic structures. So you can see here the water flows in this, and we have the hydraulic structure, and we have this hydraulic structure. So downstream of the hydraulic structure, we have these penstocks, and these penstocks, you see, we already studied the energy is generated through the turbines, but in here the water is released. We have this stilling basin. You can see here this floor which is provided downstream. This is the stilling basin. So the high energy of the flowing water, it will either flows over the spillway or can come through the tunnels, clear, as you saw in case of Tarbela Dam also in the video. You see the hydraulic jump, it is contained, so it dissipates the energy, and also protection is provided. And after this stilling basin, then the water moves in the channel without any much destruction that can cause, because it can have erosion effects. So this is how these stilling basins, these are provided. Now hydraulic jump is used for dissipating the energy of high speed flow, which may harm the environment if released in an uncontrolled way. So you can see here, this is the apron, clear? This is the apron. The hydraulic jump should occur here. So it will dissipate the destructive energy of the flow of water, and after this the water can flow with greater depth without much danger. What will happen if this hydraulic jump should take place in an area where the bottom is protected, for example by concrete slab or large size rocks? If jump take place on erodible material, the formation of the erosion hole may endanger even the foundations of the structure. So what will happen if the hydraulic jump is occurring here? So what will happen? There will be erosion of the material, removal of the material, and you can see here it will pose threat to the channel bottom, and ultimately it will endanger the stability of the structure itself. Clear? So what we do is that we provide these stilling basins. You can see here there can be different types of stilling basins. So it can include the chute blocks, the baffle piers here, and the end sill. And the idea here is to contain the hydraulic jump. So energy is dissipated, and also protection is provided against the erosion. And even if there is any problem with the turbulence of the hydraulic jump itself, still protection is provided, and after this then the water can flow with greater depth and less velocity, and it will not pose greater threat to the channel section. Clear? Now USBR has developed different types of stilling basin. You can study the documents available on the internet. Different types they develop for different types of hydraulic structure depending on the flow conditions. So you can see here, this is the USBR type 2 stilling basin, USBR type 3 stilling basin, this is type 4, and so on. We have this known as the safe stilling basin. This is San Antonio Falls. This is hydraulics lab in University of Minnesota. They conducted experiments and they developed, this is known as the safe stilling basin and Pillari's stilling basin. Clear? So we have different designs of these stilling basins. The idea is, there you can see here, made of concrete. So the idea here is to initiate the jump, to dissipate the energy, and also contain the jump. So this way, the destructive energy of the fast moving fluid liquid, that will be destroyed, and it will not pose greater damage to the channel bed, and ultimately this will increase the stability and protection to the hydraulic structure. Clear? Anyhow, we can study in detail design of these stilling basins. But stilling basins, these are not included in your textbook in detail, neither in curriculum. So we just study a brief introduction to these stilling basins. Clear? Now you can see here we have this dam. So downstream of this dam, when the water flows here, so you can see here these, here you see this different arrangement. It can be these chute blocks, you can see here, or can be the baffle piers and end sill. Different arrangements can be provided depending on the type of stilling basin. So you can see here, if you want to see the size of this is how you can imagine inspection. Clear? Of the dam stilling basin. You can see here the size of these. So the idea here is, this is for the stilling basin, and the idea is that to initiate the hydraulic jump and contain the hydraulic jump so as to protect the channel bed against the erosion, and also it will increase the stability of the hydraulic structure because it will reduce any threat that can develop. Clear? So we can study in detail the design of stilling basins when we have a course on hydraulic structure. Clear? So this was just a brief introduction about the stilling basin, the purpose. Now let us solve one problem, then I will stop this lecture here. So in a rectangular channel that is 10 feet wide with a flow of 200 CFS, the depth is 1 foot. If a hydraulic jump is produced, what will be the depth immediately after it? And part B of the question is that what will be the loss of energy? So this is easy problem. Let us solve this problem. What we are given is that the width of the channel is given, that is B is equal to 10 feet. This is equal to 10 feet. Now the total discharge, that is given as 200 CFS. This is equal to 200 CFS. The depth that is given 1 foot. Now the depth immediately after, we have to calculate depth immediately after, if the hydraulic jump is produced. So what will be the depth immediately after it? So we already know that in part A of this question, this small q, that will be equal to the total discharge divided by the width of the channel. So this will be equal to 200. This is your discharge which is given, the total discharge. So this is 200 divided by the width of the channel. It is 10 feet. So we have 10. This is equal to 20 CFS per foot. Now we already studied that Y2, this is equal to Y1 by 2. Y1 is now given. Y2 is the downstream, immediately downstream of the hydraulic jump. So this will be equal to -1 plus square root of 1 plus 8f1 square, or this can also be written as 8q square divided by g into y1 cube. So now just you need to put the values. We know the value of y1, which is given here, 1 foot, and small q we already calculated 20 CFS per foot. So you will be able to calculate y2, that will be equal to 4.51 feet. So this is the depth immediately after the jump. Clear? And in part B of the question, what will be the loss of energy? So the loss of energy we need to calculate means the specific energy at the two sections. If we can calculate before and after the jump, then the difference will be the head loss. So we already have the discharge. This is equal to V1 and Y1. Clear? So this will be equal to V1 is equal to small q divided by Y1. So this is equal to 20 foot per second. Y1 is 1. So 20 foot per second FPS. Similarly, we can calculate V2, that will be equal to q divided by y2. We already calculated y2, so this will be equal to 4.43 foot per second. Clear? Now your HL, so HL due to the hydraulic jump, HLJ, that will be equal to E1 minus E2. Clear? This is simply equal to E1 minus E2. So this HL due to the hydraulic jump, that will be equal to Y1 plus V1 square divided by 2G minus we have Y2 plus V2 square divided by 2G. So already we have the values. You can put the values here. Just plug in the values. So this HL J, this will be equal to 2.396 head loss. So this is feet. Because it is rectangular channel, you can see here it is rectangular channel. You can also apply directly this equation. This HLJ, this will be equal to Y2 minus Y1. This is whole cube divided by 4 times Y1 Y2. We already know the depth before and after the jump. You just put the values. So this will be equal to 2.397 feet. So now you can compare the two answers. You will get the same result. Now it is asked to calculate the power loss. So the power loss that will be equal to gamma Q into HLJ divided by 550 in horsepower. We have all the values here. This gamma will be 62.4. So this will be equal to 54.37 horsepower. Take care of the system of units. Remember gamma 62.4. So this is how we analyze the problem. Maybe one more problem we will solve in the coming class.